students, in this video we are going to discuss all about Dienone Phenol Rearrangement along with reaction mechanism, solved problem and exceptions. So stay with us. In this molecule we can see we have two double bonds which are known as diene and one C double bond O which is known as non. So this is a molecule we have two in and one on. If we add H plus in this molecule, we can have phenol as a final product. So what will be the possible mechanism? So if we have double bond O along with two double bonds and H plus is added, this lone pair will approach this H plus and this kind of intermediate is formed. Okay. Now this intermediate is highly unstable because we have positive charge over electronegative atom oxygen. Now we have two hydrogen in this position. If we break this CH bond, this will come here and finally this oxygen will become neutral and the final molecule will be aromatic in nature. So this is basically dienone to phenol conversion. But what about the rearrangement? We don't have any kind of rearrangement in this molecule. But if we see this molecule, we can think about the rearrangement. Okay, so this is a proper example of dienone phenol rearrangement. So again we have added H plus in the medium. So C double bond O double bond C double bond C, we have two methyl group in this position. Now if we add H plus, again the lone pair over oxygen will approach this H plus and this type of intermediate is formed. Okay, along with two methyl groups. Now to stabilize the oxygen, this pi bond will break and we have one carbocation here, and this carbocation is resonance stabilized. This carbocation is resonance stabilized, hence this pi bond will come in this side and this will be our intermediate which is going to form. Now one of the methyl group will migrate towards this carbocation and we will get this kind of intermediate which is resonance as well as hyperconjugation stabilized. Now we have one hydrogen here. If we cleave this CH bond, finally we can have our desired product by one rearrangement which is known as dienone phenol rearrangement. Okay, I hope from this mechanism you can understand the proper way of dienone phenol rearrangement. Let's solve some problem. So if we have two different groups here, what will be the proper migratory aptitude? So the migratory aptitude is given here, that is hydrogen will have maximum migratory aptitude, then phenyl, then alkyl, and in the alkyl 3 degree greater than 2 degree greater than 1 degree greater than methyl. Okay, so if we see the reaction mechanism again, then for this molecule we have hydrogen and phenyl present and this will be our case. So initially one of the CC bond will be dissociated to stabilize this oxygen and this kind of intermediate is formed. Okay, now we have two choices. We can migrate phenyl ring, we can migrate hydrogen, but according to the migratory aptitude we have to migrate hydrogen. So this H will migrate and this kind of final intermediate is formed. Okay. Now to get aromatic stabilization, one of the hydrogen will be cleaved and finally we will get this product. Okay. It is very important to remember the migratory aptitude for this reaction, that is hydrogen greater than phenyl greater than alkyl, and in alkyl we have 3 degree greater than 2 degree greater than 1 degree greater than methyl. In next problem, we have OH and methyl in para position. Thing is that we have to stabilize the carbocation in Dienone Phenol Rearrangement. Okay, so again, if we approach this lone pair to this hydrogen, we will get this kind of situation. And if we move this pi bond towards the oxygen, we will end up with this type of intermediate. Okay, now we have two choices. We can migrate methyl or we can migrate OH. Okay, if we migrate methyl, the intermediate which is going to be formed is double bond methyl OH. Okay, now thing is that this positive charge will be stabilized by resonance of lone pair over oxygen. But if we migrate OH, the formed carbocation can stabilized by hyperconjugation of methyl. But in the both case, resonance stabilization is present. But in this case, we have resonance of OH, but in this case, we have hyperconjugation of methyl. As we know that resonance effect is more effective than hyperconjugation, in this case, methyl will migrate and OH will not migrate. So this will be our case, and finally one of the CH bond will be cleaved and finally we will have this kind of product. Okay. In this question we have H plus, so lone pair over oxygen will approach this H plus. This type of intermediate again is going to be formed. Now any of the pi bond will be dissociated to stabilize the oxygen, and this kind of product is formed. Okay, now this 5-membered ring undergo ring expansion and this we have a 6-member ring along with a positive charge. Okay, now we have one hydrogen here, and if we cleave this CH bond, finally we can have aromatic stabilization. So this is going to be our final product. For this problem, again we have to stabilize the final carbocation. That is, initially lone pair will approach this hydrogen and this oxygen become positive, and at this position we have one electron donating group, one electron withdrawing group. Okay, so it is electron donating group, it is electron withdrawing group. Now we can shift these pi electrons to stabilize oxygen and we will end up with this kind of situation. Okay, now we have two situations. We can migrate electron donating group and we can migrate electron withdrawing group. Basically we think that we have to migrate electron donating group because we have carbocation, but in this case we don't have to do that because we have to stabilize the final carbocation. Okay, So to stabilize final carbocation, we need electron donating group in this position. That's why we migrate this electron withdrawing group, and this kind of intermediate is going to be formed. Okay, so this carbocation will be stabilized by the hyperconjugation and inductive effect of methyl group, and finally CH bond will be cleaved and aromatic stabilization will be formed, and this will be our final product. In this question, initially the lone pair over oxygen will approach H plus to have this kind of situation. Okay, this lone pair will approach and we will get this kind of situation. Now, to stabilize the oxygen, this pi bond will be dissociated. For this, we can draw intermediate which will look like this. Okay, again this carbocation is resonance stabilized, so this pi bond can shift and this kind of intermediate is going to be formed. Okay, now one of the methyl group will migrate and we have this kind of situation. We have one hydrogen in this position. After dissociation, this CH bond, we can have aromatic stabilization in the molecule, as well as this is going to be our final product. In this reaction, this oxygen will approach H plus. This kind of intermediate is going to be formed. Okay. Now, to stabilize that oxygen, these pi bonds will be shifted and we can have this kind of intermediate. Now this methyl group will migrate towards this carbocation and we can have this intermediate. Now this CH bond will be dissociated to regain the aromatic stabilization, as well as this is going to be our final product. Okay, this is the final molecule we are going to discuss in this lecture. It is very interesting question because we have non-aqueous solvent here, and the final product is very interesting because the reaction mechanism is totally different from our expectation. So initially, lone pair over oxygen will catch H plus. Okay, this kind of intermediate is formed. Again, this is not stabilized because we have positive charge over oxygen. Now, instead of this pi bond will shift and we can have this intermediate. Thing is that aromatic stabilization is not easy in this case. That's why this 6-member ring will undergo ring contraction So this intermediate will look like this. Okay. Again, this carbocation can rearrange itself, and again we can draw another intermediate which will look like this. Okay. Now again, this 5-member ring, to have more stabilization, will expand its ring from 5 to 6, which is known as ring expansion. And for this ring expansion, we can have another intermediate which will look like this. And finally, this CH bond will be cleaved, and we can have our final product like this: OH CH3 along with the 6-member ring. Okay, so this reaction mechanism is totally different from our prediction. Thank you for watching.